Hello everyone, today we'll be going over a deep learning course series today, and today we're focusing on neural network structures. Now, just a bit of a disclaimer, this topic is pretty dense, so we're actually going to have two chapters for our concept overview, and then we're going to have two chapters for our concept example as well to be able to help solidify our understanding, because this part is quite dense, but just a bit of a forewarning. But to be able to segue into our lesson, since today we're focusing on neural network structures, just to give a breakdown on what the structures are, let's imagine a network of neurons forming together to form a synaptic-like network, which are built with weights, biases, and activation functions. So a network of neurons built with weights, biases, and activation functions. And there's also optimization algorithms, which we will go over. Sorry. Algorithms, which test the model's accuracy and prediction. And there's also a variety of activation functions, which we will go over in the second part of our concept overview, along with the optimization algorithms as well. And so, mind you, what we will be breaking down is that we're actually going to be breaking down some of the mathematical concepts inside of neural networks. So this does require a fundamental basis between linear algebra. You can also pick up some combinatorics and calculus as well. But from a fundamental standpoint, since neural networks are comprised of vectors, mainly for input, weights, biases, and activation functions, to be able to build up to an understanding over vectors, one would need to start with matrices, scalars, and then the vectors to be able to garner and further grasp a foundational understanding between the math that is already here. I am doing a linear algebra playlist to be able to go over exactly those fundamentals as well, along with combinatorics and calculus as well. However, for now, we are just giving a structural overview to garner a grounded understanding between how neural networks are built from a foundational, formulated, and structured standpoint. And so just to be able to give a breakdown of neurons, and this is our neuron function that we have over here. Neurons or nodes are individual processing elements of a neural network. Neurons. Like the human brain's neurons, which fire off electrical signals, these artificial neurons receive input, process it, and pass on the output. So the process data for desired output. Weights are in a neural network, and input data is fed into the input layer, consisting of many neurons as there are features in the dataset, and each input neuron sets its signal to the neurons of the next layer, which could be a hidden layer, or in simpler networks, the output layer directly. And we always know that every single neural network is comprised of three components. We have our input layer, one or more hidden layers, and then our output layer. The input layer is where the data is already being fed in. The hidden layer, it could be one or more, depending on the complexity of a problem. Then we have our output layer as well. And to give a breakdown on the math really comprised of neural networks, this is just really focusing on a neuron that we have here. So neuron will be denoted as Y. F is known as the activation function. And then weight of I refers to the weights in the connections to the neuron. Weights of the connections to the neuron. As in the next one or the previous one. And then x of I is going to be referring to the input values. And B is referred to as the bias term. And N is comprised of, this is the number of inputs for the neuron. Inputs to the neuron. And so, just break that. Oh. There we go. Just for reference over here. Weight, input, bias, number, and this is just a summation of everything all together. And now to give a breakdown on a specific neuron, specifically with weights and biases as depicted in the first picture. So we have our weights as depicted right here based on the inputs that we have within a given data set. And then we have our bias as well and have the summation function leading to our activation function to then have a prediction. So specifically with weights and biases, as depicted in the first picture, weights are parameters that determine the strength of the connection between the two neurons across different layers. So weights, parameters that determine the strength of the connection between two neurons across different layers. When one inputs data into a neural network, and each piece of information or feature is multiplied by a corresponding weight as it moves from one layer to the next. And these weights are crucial because they influence how much impact each input feature has on the network's final output. And to go over the weight matrix, the weight matrix is a structured arrangement of weights that represents the connection between two layers of neurons. And through the training of neural networks, we are processing the input data, as depicted up here. During the forward pass, just going through, when the network processes input data, the input vector, which is representing the data, is multiplied by the weight matrices of successive layers. And this operation computes the weighted sum of inputs for each neuron in the next layer, and this result is then typically passed through an activation function before proceeding to the next layer. Since using matrices to represent weights not only helps in organizing networks architecture, but also leverages efficiently for computational libraries optimized for matrix operations. And to give a breakdown over our matrix operation, for our weights, W is going to stand for the weight matrix itself. And then for M and N, so W for this W over here represents the matrix single matrix, the matrix single weight. Actually, we'll just call this a single weight. So with M refers to number of neurons in the layer where the output will be calculated. And N is the number of neurons in the previous layer that provides the input. So number of neurons in the previous layer for our final output. And then meanwhile, for the following numbers beforehand, we're going to refer them as I and J. So if we have I and J over here, I refers to the index of neuron in the current layer. While J is the index of the neuron for the previous layer. I and J. So that's just a breakdown of our weight matrix. Now biases, on the other hand, so we already denoted what the weight is. Let's move this over here. Biases, on the other hand, allow the model to adjust the output. Of each neuron, depending on what data is fed, will activate the neuron. In the neural network. Oh. In the neural network. So this means that biases enable the neuron's activation function to activate or fire at different input values, essentially shifting the activation function left or right, depending on exactly what data is already fed inside of the neural network. Even if the data does not directly align with the origin, or if the relationship between the inputs and outputs are complex and nonlinear, the biases serve an essential function to be able to activate for neurons as well. And now, moving deeper into neurons, we'll be focusing more on the hidden layers. So hidden layers they form the training area for the model as the collection of neurons and these layers can be numerous, and their complexity can vary vastly depending on the task that one is already applying. And as data moves through each layer, it's transformed, getting closer to a decision or prediction with every step. So each step of data moves. Hang on. As data moves through each layer, hidden layer, the model discerns the probability of prediction. All right, and now going over the next part, now that we've already discussed between weights and biases between the two, as well as the structure of the neural network, we're moving over to activation functions and optimization algorithms for a brief overview of what they are. Activation functions, let me just zoom in. And there's a variety of them that we're going to go over in the next part. Activation functions are considered a catalyst within the system, and they decide whether a neuron should be activated or not. Decide when a neuron, also as denoted here, that's our activation function. Activation functions decide when a neuron should be fired or not. And they essentially determine the output of that neuron to the next layer. And these functions introduce nonlinearity into the network, enabling it to learn and perform more complex tasks than a simple linear regression could. More complex tasks than linear regression. And we'll be going over the common types of activation functions in the next part. So that's just a brief overview of activation functions. But then the next part that we have, we'll be focusing on optimization, optimization algorithms. So optimization algorithms Optimization algorithms are applied after each activation function is considered for each neuron. And when they're applied to each neuron during training, they measure how well the model's predictions align with the actual data. So they measure how well the model's prediction aligns with actual data. And the goal for optimization algorithms are to find the set of parameters which were included in the context of the model to match the best possible predictions by minimizing the loss function. So, which the loss function is considered chances of inaccurate predictions overall. So they are focusing on providing the best possible predictions for the model while reducing the size of the loss function. So just focusing on accuracy and prediction for the given model. And overall, optimization algorithms are crucial for training because of its application in backpropagation. So strong application. So I mean, like, they really are. So application in backpropagation. And during training, the network uses backpropagation to adjust the weights based on the error of the output. So adjusting weights as indicated by our matrix, depending on the output. Depending on the error of the output. Let me just erase this. Depending on the error of the output. And overall, this involves calculating the gradient of the loss function gradient of the loss function with respect to each matrix versus weight. All right, here we go. Let me just clean this up for you folks so you just get a full understanding and are able to see everything all at once. Give me 1 second. All right, and feel free to take a screenshot of the following. And now let's move over to our second part for our concept explanation, where we are going to be going over the specifics of the different varieties of activation functions and optimization algorithms. And now let's go over the second art for our concept explanation for neural network structures. Now this time we'll be going over activation functions and optimization algorithms. And we're just giving an overview for the most common ones actually used for deep learning model development. So to start with activation functions, the most common ones are typically going to be sigmoid, the hyperbolic tangent function, the rectified linear unit or ReLU, the leaky ReLU, and or softmax. And I have the following acronym down here for memorization, STRL-RS. To be able to go off, you can make any type of acronym you want to be able to memorize, but this is just a brief overview, and we'll be going further in depth for each activation function. And to start, the first one to explain will be the sigmoid function. Now, the sigmoid function, also known as the logistic function, produces an S-shaped curve. Let's get rid of these. So this sigmoid function, or sigmoid functions in general, is a logistic function. And it takes any real value number and maps it in a range between 0, that we have over here, and 1. But not exactly to the boundaries of 0, 1, just for context. This characteristic is useful when the function is used to model the probability in binary classification. So great for binary classification. At high positive values of x, so on the x-axis that we have over here, as the sigmoid function produces more positive values, the function approaches 1. We see on the y-axis, as it goes up and up and up and up, it's going to get closer to 1, and this indicates a high probability of the positive binary classification, so high probability of positive classification. Let me just make this really quick. High probability of positive classification. Conversely, as the x is approaching a higher or lower negative value, such as -5, -10, -100, this would represent the high probability of a negative probability in binary classification. So negative probability of classification. Since we already noticed that the value, the y value, is approaching closer and closer to 0, as we have more negative values in the x-axis, conversely with the higher probability, as there are more positive numbers. We notice this correlation over here. And the function's output can be interpreted as a probability because for any given input value of x, the output value is between 0 and 1. And the total sum across multiple sigmoid functions can be normalized to sum up to 1. So, classification between 0 and 1. And to give a breakdown for each of the following symbols for the sigmoid function, I'm going to use a different color. So we have the sigmoid function over here. And then we have x, which represents our input. Then we have Euler's number as well. So sigmoid X is our input, and E is going to be Euler's number. Which is roughly 2.71828. Let me just zoom out of here. There we go. And then feel free to take a screenshot of this part, and we'll be focusing on the hyperbolic tangent function. Now, to go over the hyperbolic tangent function, the hyperbolic tangent function outputs values in a range from -1 to 1, as we see over here, making it zero-centered, which can help with the convergence during the training of neural networks, which means reducing the chances of error between the different outputs during the training process. So, it helps with convergence, reducing the error during training, for neural networks. And this function behaves much like the sigmoid function when x is near 0, as we see with the S-curve. But as x moves away from 0, the hyperbolic tan function approaches to -1, as we see for negative values, and 1 for positive values, more sharply than the sigmoid. This steeper gradient can lead to faster learning in the early phases of training, but much like the sigmoid function, the hyperbolic tangent function also suffers from a concept called vanishing gradient. A little side context, may suffer from vanishing gradients. For vanishing gradients, basically have smaller values as they are approaching closer to a specific value that we have on the y-axis, and this could lead to slower learning if the gradients are very small, since during the training process weights and biases are constantly updated throughout the training process, hence the term convergence. And as a result from slower learning, this would actually have not that much of a significant change between the weights and biases, making the training process extremely slow. So, slower training. And also a bias towards recent data. Where vanishing gradients can cause a model to have a short memory, and it fails to propagate learning signals back to the earlier data points in the sequence, and just in those contexts as well. But to be able to go over the formula for the hyperbolic tan function, is that the hyperbolic tan function, typically we have our symbol, tan h of x. Then we have the Euler's number that we already know. So we have E, Euler's number. Then we have x as our input to the function. Hyperbolic tan function. There we go. And overall, much like the sigmoid function, the tan function operates as a unique way to be able to train neural networks as well. So let me just zoom out of here, and feel free to take a screenshot. And moving over to rectified linear unit. Now, the rectified linear unit is perhaps the simplest nonlinear activation function used in neural networks. For any positive input, it returns the value directly. So, for any positive input, it returns the value directly. However, for any negative input, it's obviously going to return 0, as we see in this graph over here. This creates a sparse activation pattern, which is computationally efficient and allows the network to easily obtain and operate with a derivative, except for the point at 0 over here, when the function is not differentiable. ReLU units can be more robust to the vanishing gradient problem, especially for deep networks, because the gradient is either 0 for negative inputs or 1 for positive outputs. Great for binary classification, as usual. And 0 for negative inputs. And to go over the symbols, so ReLU, we already know that it's that direct function that we have, but really we just have x as the input, as we already know, and then we already know between 0 and x, between what we already given, so we would have 0, 0 in that case, and we would just get the max between those two values. Now, the leaky rectified linear unit improves upon the idea of the ReLU function by allowing a small non-zero gradient when the unit is not active, less than or equal to 0. So we notice in this negative, right here, it leaves some extra room. So we got some extra room for negative values. As our input. We see the difference over here, so that's ReLU, it's 0, but here, in this case, we have a leaky ReLU to be able to ensure that when there is a negative value, the slight slope ensures that even the dead neurons, those that only output 0 in ReLU, have a chance to update and contribute during the training process. So the reason for the slight slope is to allow negative values / dead neurons to contribute during the training process. As there is always a gradient flowing through them, so that is why in particular. So neurons, I would say all neurons have a gradient flow through them. Now, to give a breakdown of the symbols for the ReLU, for the leaky ReLU, so we already know that x is going to be our given input, if x is greater than 0, and then the following symbol is a small constant. For negative values. Alpha typically is set to very small values as well, such as 0.01 to determine the slope of the function for negative input values, and this can be crucial for maintaining alive neurons in the network. So alpha incorporates all possible alive neurons during the training process. And finally, we have the one and only softmax function. And the softmax function is a generalization of the sigmoid function for multiple classes. So generalization of the sigmoid function for multiple classes. For a given vector of x of real numbers, the softmax function normalizes it to a probability distribution consisting of softmax x of I that we have for a given input. The output is a vector of the same dimensions as x, where each element ranges between 0, as we already know over here, or right over here, that's sigmoid, so we have 0 over here, and then 1. And all the output values add up to 1. This function is widely used for multi-class classification. For multi-class problems where it can be providing the probabilities of different classes for a single input. Probabilities of different classes for a single input, and is typically placed in the final layer of neural network classifiers. Placed in the final layer for neural network classifiers. And to go over the following symbols as well. So the softmax function, we typically have E for Euler's number, and we have x of I, which refers to the ith element of the input vector. And J is the index. J is the index used for the sum of all elements in an input vector. So let me just clean this up for you folks so that way you can see the whole scope over what we're talking about. So just give me 1 second. Now for optimization algorithms determine if we are going to have a negative probability or a positive probability based on the input of the data in respect to the weights and biases. This is a separate calculation from the activation function. And then right here, optimization algorithms play a significant role in shaping the behavior. So they shape the behavior of neurons within a network, ultimately just grouping them together between negative and positive probabilities. They guide the learning process by adjusting weights which indirectly affect the probabilities associated with neuron activities to determine if a positive or negative probability is occurring. And these probabilities can be thought of as the likelihood of a neuron producing a positive or negative output. So we are just grouping probabilities together. Through the iterative process of training, optimization algorithms group neurons together based on their behavior, influencing whether they tend to produce positive or negative probabilities, and this grouping is essential for the network to learn and make accurate predictions. Overall, with respect to the weights and biases from the parameters set by the model, we're able to understand the network's overall performance. So, and also for further context as well, optimization algorithms are widely used, especially in a method called backpropagation, which we will cover in a future video focusing on the training of neural networks. But right now we're just focusing on the overall structure behind the process of a neural network prior to going further depth in the training. But again, for future reference, we will have that video. And common optimization algorithms used for the process would be gradient descent, stochastic gradient descent, mini-batch gradient descent, ADAM, which stands for adaptive moment estimation, RMS prop, which means the root mean square propagation, AdaGrad, which means adaptive gradient, AdaDelta, adaptive gradient delta, and improvement over AdaGrad, and NADAM, which stands for Nesterov accelerated adaptive moment estimation. And we have the following acronym over here. Now, to be able to go over and understand further in depth between gradient descent is a first-order iterative optimization algorithm used to find the local minimum of a differentiable function. The idea is to take small proportional steps in the direction of the negative gradient, the steepest descent, of the objective function with respect to the model parameters. So we are looking for the steepest descent of the objective function and this is technically called gradient descent because it uses the information of the gradient, the steepness of our given slope, to decide the direction, and descent because it aims to descend to the lowest point. So it is descending to the lowest point. As well. And the learning rate defines the size of these steps, and choosing the right learning rate is crucial, as too small of a rate can lead to slow convergence. Also, we have to be crucial about the learning rate to avoid slow convergence. And if we have too large of a gradient descent, that means we would overshoot. Shoot. The output. There we go. And to be able to break down how the formula is actually built and constructed, so theta refers to the parameter vector of the model, which needs to be optimized. And the following symbol refers to the learning rate, which controls the size of the steps taken towards a minimum loss function. So controls the size of steps taken forward to minimize, or to the minimum of the loss function. And this following group over here, J theta, refers to the gradient of the loss function, referred to as J, with respect to the parameter vector. Respect to the parameter vector. One second. And now let's over to stochastic gradient descent. So stochastic gradient descent is a variation of gradient descent, except for it runs faster by updating the model's parameters using only a single sample. So stochastic calculus is, stochastic gradient descent is like gradient descent. It processes faster though. Alright, by updating the model's parameters to use a single set. Slash subset of the full data set. This allows for much faster iterations, but the trade-off is that the updates are noisier. which can lead to resultant fluctuations and potentially only converging to a neighbor of the minimum rather than the minimum itself. Stochastic gradient descent works well when the dataset is large and redundant, so works well with large and redundant data, as the noisy steps can help to escape local minima and possibly leading to better generalization of unseen data. Better generalization of unseen data. And to go over the symbols, so stochastic gradient, theta, is the parameter vector. Eta, this symbol, eta, is the learning rate. And then this bad boy here, x for I, then y, I plus b, which is the gradient of the loss function with respect to theta. With respect to theta. Stochastic gradient descent is evaluated at a single set of the full data set. There we go. And now let's head over to mini batch gradient descent. And so mini batch gradient descent is an algorithm in the middle ground between batch gradient descent and stochastic gradient descent. So it is between batch gradient descent and stochastic, stochastic gradient descent. In mini-batch gradient descent, the update of the parameter is performed on a small random subset of the full dataset. So it utilizes a small random subset of the full dataset. Utilizes a small random subset of the full dataset and updates parameters. This combines the advantages of both stochastic gradient descent and batch gradient descent by reducing the variance of the parameter updates. So, reduces variance on parameter updates leading to more stable convergence, and by being more computationally efficient than using the full data set. Lead to stable convergence. Then using the full data set. The size of the mini batch is a hyperparameter that can affect the performance of the convergence speed. So the size of the hyperparameter affects speed. Affects convergence speed. And to go over and break down the following symbols that we have. So mini batch gradient descent, the following symbols are. So you have theta, which we all know it's going to be the parameter vector. Eta is the learning rate. And then this bad boy over here. I wonder if I could just copy and paste the whole thing. I think I can. Let's do that. Just write it out. There we go. That's better. That looks prettier. This one is the gradient of the loss function. With respect to theta, as well, evaluated a small subset batch. And for evaluated at small subset batch. And now let's move over to the ADAM, or adaptive moment. Now to go over the adaptive moment estimation, or ADAM optimization algorithm. ADAM is an adaptive learning rate optimization algorithm designed specifically for training deep neural networks. It combines the advantages of two other extensions of stochastic gradient descent. First, so combines two components of stochastic gradient descent First, similar to the root mean square propagation optimization algorithm, it maintains a per parameter learning rate that improves performance on problems with sparse gradients. So like natural language and computer vision problems. So maintains a per parameter learning rate which improves performance on problems with sparse gradients. So it's thorough. Second, similar to stochastic gradient descent with momentum, it also keeps track of the decaying average of past gradients. So it keeps track of decaying averages for past gradients. However, Adam also computes the decaying average of past square gradients. So, calculates the decay average of past squared gradients, which is used to scale the learning rate for each parameter. And this means that parameters with large gradients will have their efficient and effective learning rate be reduced, while parameters with small gradients will have their effective learning rate increased. So increases / decreases learning rates for small and large, respectively, gradients. So we focus on speed and accuracy of prediction while minimizing the loss function. Focus on speed and thoroughness for training. Adam overall usually requires little to no manual tuning of the learning rate and often works well with default settings. No manual tuning needed. And now to go over the formula. Adam is comprised of M MT view T M T T. We have beta 1, it looks like. U. And then epsilon as well. So M of t represents the first moment estimate. V of t represents the second moment estimate. M cap t represents the bias corrected first moment estimate. Bias corrected with first via t, and bias corrected second. Beta 1, exponential decay rates for moment estimates. Rates for moment estimates. And then we have our learning rate. Learning rate, and epsilon represents a small constant to prevent division by 0. And now let's head over to root mean square propagation. And feel free to take a screenshot of each of the components of our optimization algorithms. And now going over root mean square propagation. Root mean square propagation is an adaptive learning rate method designed to result in radically diminishing learning rates, commonly in autograd. So it's an adaptive learning rate improvement from autograd. And it does so by modifying the general gradient descent by dividing the learning rate for a weight by a running average of the magnitudes of recent gradients for that weight. So modifies the general gradient descent and by dividing the learning rate for a weight by a running average. So learning weight. Oh. For a weight. By a running average of the magnitudes of recent rates. So recent running average, or running average of recent. Gradients. For the same weight. This means that the algorithm divides the learning rate by an exponentially decaying average of the squared gradients, hence the square root. And this operation prevents the learning rate from decreasing too fast. Prevents learning rate from decreasing too fast. And is beneficial for problems with very noisy / sparse gradients. So Very useful for noisy/sparse gradients. And root mean square propagation can work well in scenarios where autograd falters due to aggressive and monotonically decreasing learning rates. So we got a good speed of learning rates. For higher accuracy. And to go over the symbols for root mean square propagation, the following symbols we have will be, we have e of g squared with the absolute value with respect to time. Which the running average of the square gradients. And then we have mu. We have the following symbol, as we know, which is the learning rate. Then we have epsilon, a small constant for numerical stability. Constant for numerical stability. And G of t which equals the gradient of the loss function with respect to the input vector at a given step in time. So gradient of loss function with respect to the input vector represented by theta at time step t. What is... Alright, there we go. Now let me just clean this up. There we go. And let's move over to our next part, autograd. Now to go over adaptive gradient descent, or the adaptive gradient algorithm, autograd is an algorithm for gradient-based optimization that adapts the learning rate to the parameters. So, gradient-based and adapts the learning rate to the parameters, performing larger updates for infrequent and smaller updates for frequent parameters. Perform larger updates for infrequency infrequent parameters and perform smaller updates with frequent parameters. It is particularly suited for dealing with sparse data, so great for sparse data. The benefit of Autograd is that it eliminates the need to manually tune the learning rate, as we discussed before. However, its accumulation of the squared gradients in the denominator can lead to excessively rapid decrease in the effective learning rate. And it can prematurely converge to suboptimal solutions, which is why it may not be well suited for training deep neural networks, but it is good to be able to know whenever we have sparse data that we can use the adaptive gradient descent if we need a quick means of classification. So it's faster for optimizing classification, trade-off with speed and accuracy. And to go over the following symbols to help break down, it will be the following. Let me just move this up. All right, the following symbols will be for Autograd. So G of T I is equal to the sum of squares of gradients with respect to theta up to time step t, and then mu refers to, as we know, the learning rate. Epsilon is a constant. Constant to prevent division by zero. Similar to the root mean square propagation. And finally G of T, lowercase. So we have this symbol right here, G of T. With respect to the input, it's going to be the gradient of the loss function with respect to input vector and at time step t. me just clean this up for you folks. And now let's move over to our next part, ADA delta. So ADA delta, or adaptive gradient delta, is an extension of AdaGrad that seeks to reduce its aggressive, monotonically decreasing learning rate. So, extension of AdaGrad, but decreases monotonous nature of speed with AdaGrad. Instead of summing up all past square gradients, ADA delta restricts the window of accumulated past gradients to a fixed size. So establishes a fixed size using only the most recent gradients, unlike summing all past squares. This makes it robust to the main weakness of AdaGrad. The ADA delta update rule is similar to the root mean square propagation, but with a more sophisticated way of changing the learning rates. It eliminates the need to set a default learning rate, which is a significant advantage over AdaGrad and root mean square. So it changes the learning rate. For more adaptive data that isn't as monotonous and no default learning rate, keeping the speed but considering noise. Let's go over the symbols. So the following symbols that we have for ADA delta will be the following: E of G squared as a value with respect to time versus running average of square gradients. The following symbol here is P, refers to the decay rate similar to beta. In atom optimizer. Then we have delta theta t, which is a parameter update vector at a specific time. Vector at time step t. And then epsilon, on the other hand, A constant for numerical stability. Constant for numerical stability. And now let's head over to our next part. Feel free to take a screenshot. But now we will be adapting to our next optimizing algorithm, Nesterov accelerated adaptive moment estimation, or NADAM. So NADAM, or Nesterov accelerated adaptive moment estimation, combines the benefits of Nesterov accelerated gradient. So combines Nesterov accelerated gradient and Adam optimizer. So we have Adam and Nesterov accelerated gradient. I'll also have a link for that. By incorporating Nesterov momentum into Adam. So they combine Nesterov momentum into Adam, and taking into account the look ahead property of Nesterov. So they combine momentum and look ahead. Property. This helps to not only gain the benefits of the adaptive learning rates from Adam, but also the accelerated gradient from Nesterov. So strong, beneficial learning gradient. From Nesterov. And adaptive learning rates from Adam. So we speed and thoroughness. And overall, it makes it more efficient than any other of the following solo methods alone. NADAM has been shown to outperform Adam, actually, in some cases, especially in problems with very noisy gradient or with problems with fine-tuning of the solution. So, works very well with noisy gradient or problems requiring fine tuning of solution. And so let's go over the symbols. There we go. So for the following symbols, NADAM has MT, M cap, T, G cap, T, beta 1, nu, V cap t, and epsilon. So let me just move this over a little bit more to be able to help. There we go. No. Okay. So M of t is running average of the gradients. M cap t is the corrected running average of the gradients. G cap t is gradient of Nesterov momentum. Beta 1 is the decay rate of momentum. Term. U is, as we know, the learning rate. V cap t is the running average of the square gradients, so running average of squared gradients. Epsilon, a small constant to avoid division by 0. Let me just clean this up now. There we go. Feel free to take a screenshot. And now we will move over to our concept examples. And now let's go over our concept example. So to give a real life analogy, let's imagine a company's hiring process. Now, mind you, for every single neural network that we have, we always know that a neural network has 3 components. We have an input, one or more hidden layers, and then finally the output. Let me just move that. And training of the neural network. Work and focusing on one specific neuron is that one neuron is always going to be equal to the activation function times the sum of all of the following weights of the inputs and the input value plus the bias to the power of the number of the inputs of the neuron for each component. And when training, we have weights, biases to consider, and an activation function. It's highlighted in the neuron formula here. And we wrap that all up with an optimization algorithm. There'll be more further in-depth videos talking about the training of a neural network. But right now, this is just an overhead overview and just to be able to understand the structure of neural networks. And so when we are imagining a neural network with an HR team, we are going to be imagining that that the neurons are going to be the HR team, the layers, one or more hidden layers, are going to represent the stages of the hiring process. And the activation functions are refers to the decision criteria. And the output determines if the person is hired or not. So it's a hiring decision. Hired yes or no. Or just ask ourselves, should we hire this person? Initially, resumes are screened based on the experiences and skills, and this is the input layer. So input layer, initial screening. Next, the selected candidates undergo several rounds of interviews. These are the hidden layers. Stages of the hiring process and interview rounds. And where we understand more about the evaluation that occurs. Finally, the hiring decision is made, as we have said, from the output layer. So that's where the magic happens. And at each stage, certain criteria must be met for a candidate to proceed, like the activation function determines if a neuron signal should pass to the next layer. All right, so, and activation function. Determines if a neuron should proceed to the next layer. And then going into our further concept understanding. So the steps for us to be able to actually put out inside of our model is that one, we already initialized the following libraries. It looks like we're going to be importing a sequential model as well as a dense model as well from the Keras libraries and the dense layers really from the Keras layers part and the Keras models that are also available. So we're employing a sequential model along with dense layers for our following model that we're applying. So after we have imported, we're going to assume that X is the input database with multiple features and Y is the output of the labels. For every instance of X, could be a matrix of the application of resumes with features such as the years of experience, skills, range, etc. And Y could be binary labels indicating whether the applicant was hired, 1, or not, 0, based on the criteria. So initially, we would load our data. Then we declare our model, and this is where the hidden layers and all the layers go through. It looks like, so initially the sequential model we have right here, we initialize it and allows us to build a model layer by layer. And this is where we add the input layer, which corresponds to screening resumes on experience and skills, such as we have 10 features we look at, hence 10 input neurons. This is our input layer that we have. Then the hidden layers go. So we have layers, and then this part hidden. So adding a hidden layer, which is akin to the first round of interviews in the hiring process, We use 15 neurons, arbitrarily chosen for the purpose of this example, and the ReLU activation function, which we already went over in our activation function section / video. If needed, we can add more hidden layers, each representing subsequent rounds of interviews. So for this example, we'll add one more hidden layer. So we have a second hidden layer, one hidden layer, and adding the output layer represents the final hiring decision. We use one neuron since the outcome is binary, hired or not hired, and the sigmoid activation function. And we use one neuron since the outcome is binary. And we compile the model with a binary cross-entropy loss function. Let me just actually fix this over here, because technically, so all these parts are going to be layers. Let me clean this part up. So this is our input layer, and then that part is hidden layer. Then we compile, and it looks like we're using the Atom optimizer as a good default choice for general purposes, and it's great for binary classification. And we summarize the model structure, which helps us provide the visual neural network layers and neurons. And at this point, we would train our model with application data, not shown in this example, since we don't have that much data, and this is just a given example that we have. So we have a batch size of 32 with 100 epochs as well. After training, we could evaluate our model's performance, akin to reviewing the hiring process effectiveness, and then we make our predictions for new applicant data, such as once we put it in and already trained the model accordingly, just based on the Keras library that has already been expansive, we can put in new data to be able to put inside of our following model that we have already put. So it's calling upon the model to predict based on the data. It's going to run the sequential model through the input layer, hidden layers, compile, and have the loss function as well to summarize. And then and this is the training part. To fit our batch size data. Let me just zoom out and clean up for you folks. And actually, if you want to take a screenshot of this part, by all means do so. And just move it out right now. Let me see if I can make this bigger. Okay. Yep, so there we go. Let me just clean this part up. There we go. And now let's head over to our second concept example. Now for our second concept example, let's imagine a tech company called Tech Guru Inc. is looking to hire a software developer. They receive hundreds of applications and need to decide whom to interview and eventually hire. To manage this, they set up a multi-stage process that resembles the layers of a neural network. And so, in order to be able to understand more, we always know that a neural network is going to have three components to it. We got the input, one more hit. We got the layers, then we have the output, respectively, and also as well for all the neurons that we have, as indicated by our formula as usual. We're going to have weights, biases, activation function, and afterwards an optimizer or optimizing algorithm. And so, in order to resemble the whole components of the hiring process, this is what we will go over. So we always have the input layer, which could be represented as a resume screening. Then we have hidden layer 1, hidden layer 2, hidden layer 3, an output layer, respectively. So hidden 1 could be the phone interview. Then the next part is technical assessment. Hidden layer will be the on-site interview. Finally, the output layer is the hiring decision based on the pattern. And so the input layer refers to the initial screening of applications, serves each neuron in this layer represents a criterion such as years of experience, programming languages known, education level, and so on. We focus on our features. To filter. Just as neurons in a neural network take various input features, the HR team reviews these aspects on each resume to decide if an applicant proceeds to the next round. This is similar to input neurons processing features and passing the information forward. And for the hidden layer, the first one, which is the phone interview, applicants who pass the screening are then given a phone interview, which represents the first hidden layer. In this round, the HR team probes deeper, asking about past project experiences, problem-solving skills, and team collaboration. Each neuron, indicated as an interviewer, may focus on a different skill set, activating only if the applicant's response exceeds a certain threshold. So, activating a specific neuron with respect to a specific threshold. And it's akin to the activation function in neural networks that decide whether the signal is strong enough to be passed on, much like the activation function. Then, the second hidden layer refers to technical assessment, where a smaller group that succeeds in the phone interview moves on to the technical assessment. This stage serves as the second hidden layer, where candidates' coding abilities are tested, they're given a set of programming problems, and their solutions are evaluated for logic, efficiency, and creativity. Here, the neurons are the different problems, assessing the various aspects of the applicant's technical acumen. Then, for the third hidden layer, which is the on-site interview, the very best candidates are invited to an on-site interview. The hidden layer for where they meet multiple team members. They are assessed for cultural fit, team dynamics, and communication skills. Like a neural network that abstracts and refines information layer by layer, the interviewers synthesize a broader picture of each candidate's potential fit for the role. So for the third one, neural networks abstract and refine information. And finally, for the output layer, which would be considered the hiring process and hiring decision, the final stage, considered the output layer, is when the company decides which candidate or candidates are extended an offer. The neurons in this layer integrate all the information processed from previous layers, the results from the interview, assessment, and initial resume screening to activate a hiring decision. So the grand finale for decision, accumulate all data from neurons for output and minimized loss function. And then through this process, just like the neural network, each stage refines a pool of candidates, and the activation functions could be thought of as benchmarks or cutoff points for deciding if a candidate advances to the next stage or not, since every single layer is going to have to consider an activation function. Since if we go over a formula, we always know that every single neuron is multiplied with the activation function. So, for example, the requirement might be at least 5 years of experience to pass the resume screening in the input layer, or a minimum coding test score to move on to the from the technical assessment to move on to the next layer, and so on and so forth. And these thresholds help filter out candidates at each layer, similar to how activation functions filter out signals that are too weak to contribute to accurate predictions. So, activation functions filter out weak signals to contribute to accurate predictions. And this multi-layer stepwise filtering process closely mirrors how a neural network operates, with each layer making decisions based on the output of the previous layer, ultimately leading to the final outcome for the decision. It's a system designed to handle complex decision making by breaking it down into simpler sequential equations. And so if we were to go over our whole overview between how this would already be set up. So one, let me see if I can just minimize this for side-by-side comparison. 1 second. There we go. All right. And so, initially what we have for our input prior to would actually be one, we already call upon libraries to call upon neural networks we would add, and we assume that we have a data set where each applicant's resume is encoded into numerical features, where we have X equal to the applicant features, a matrix where rows are applicants and columns are features, skills, and experience. X applicants, yep. And Y equals features. Y is equal to features. Remember that? Where y in this case is considered hired or not. Where y is considered hired. No. And y is considered hired. Or not. And this would be considered a binary classification where we will have a binary vector where each element is 1 if the applicant was hired and 0 otherwise. So we would have this function to be able to load the data. We would have a specific file name to load it, depending on what format we put it in. And then we are splitting the data set into training and testing to evaluate the model. So it looks like we're going to be doing a 80-20 split, where we're also calling upon scikit-learn model selection to import the training test split. The libraries are pretty efficient to be able to do so. So random state of 42, and we normalize the feature data in particular from what we are looking for, and we are implementing standard scalars to be able to fit and transform the data to be able to see exactly based on the features that we're getting from the applicant. We call upon a sequential model to build a network model, and it looks like we have our layers that we have already set in place. We got our input layer, hidden layers, and then we have our output layer. When we have done so, we then compile the model, and it looks like we're using the atom optimizer, and for a loss function we're using binary cross entropy to be able to predict the accuracy of the model, and then we summarize the display for the model. And we train the model with application data to be able to fit in what we have already trained and scaled based on hiring or not based on the following features. We're doing 100 epochs to be able to train the following model and fit. And we do a batch size of 32 with a verbose of 1. We then evaluate the model's performance, and this could represent how well the hiring process proceeds to job performance overall to be able to predict accuracy. And we make predictions with new applicants and new data, as we've already called. So we have new applicant data that we will be calling to then forward in for a hiring decision process. So new applicant data should be pre-processed in the same way as X-trained accordingly. And then we make a hiring decision for the model to predict new applicant data. Right over here, we make that. Hiring decision will already be able to execute for model predict new applicant data. And so let me just zoom out of this. There we go. And feel free, let me just move forward here for the coding part that we've broken down. Feel free to take a screenshot of this. Feel free to take a screenshot on the right as well. And pause the video to do so. And let me just move this. Our basics on understanding. There we go. And also for the left as well. There we go. And now let's move on to our first practice problem. And now for our first practice problem. Let's imagine we're creating a neural network to identify spam email. The network's input layer receives email features such as frequency of specific words, sender reputation, and usage of exclamation marks. The hidden layers must discern patterns, what combination of these features typically indicates spam, and the activation functions at each neuron in these layers will decide whether the pattern is strong enough to consider the email spam, influencing the final output spam or not spam. So to go over, we are doing a neural network. Okay, come on. For spam email. When doing so, we have the following for a neural network: input, layers, and output. And as we know, that every single neural network's neuron that we have already set up in place is going to have weights, biases, and activation functions set in place with an optimization algorithm. And to go over what we just discussed, so for our input layer, if we were going over the specifics of the layer, since that is where the training process happens, the input layer for one is going to set the features and the hidden layers will discern patterns, which combination of these features typically sends spam, so ultimately discerning features, and the activation function at each neuron in these layers will decide whether the pattern is strong enough to be passed from one layer to another. Determine if pattern is strong enough to pass per layer. Hang on one second. There we go. And so, let's just go over the following steps that we need to be able to construct this. Step 1, input layer configuration. Step 2, design the hidden layers. Step 3, choose activation function. Step 4, train the network. And those are our steps to do. So when we input the layer configuration, we begin by setting up the input layer with neurons equal to the number of features we've identified as significant. So we identify significant features. Each feature of, for instance, an email, such as a text length or a number of hyperlinks it contains, is fed into the respective neuron. So features are fed into respective neuron. And the step is critical as the quality of input directly impacts the network's ability to learn effectively. The second part, next we need to configure the hidden layers, which refer to the number of layers and neurons per layer require careful consideration, as this architecture will capture the complexity of our problem. We must strike a balance where too few neurons may not capture the nuance of the spam, while too many neurons may lead to overfitting. So we need to consider number of neurons for few neurons inaccurate. Well, I mean, they're both going to be inaccurate. Like, overfitting really is just making a wrong prediction based on those features, given the fact of the data that it's specifically trained on, hence overfitting. If we were to have an untrained piece of data fed into the neural network, it would categorize it into completely something else. But it's just been so well trained in the features that we have already set up in place, it's going to focus solely on those features. So that's what the premise of overfitting is. So we're fitting too well trained in features. In specific features. Or too few. So few neurons are not able to categorize spam. Or whatever context you want to put it. Then the third part, choosing an activation function. Now that in this part we select an activation function for the neurons for a specific detector. In this case, we're going to be using the ReLU one. So yeah, so ReLU activation function could be a good choice for hidden layers due to the simplicity and efficiency. However, for the output layer, we might use a sigmoid function since our final decision is binary spam or not spam. So we can do a sigmoid for the sake of binary because this is always the most convention. So depends on context problem. Context of problem. And what specifically you want to output. Want to output. And when we train the neural network in our fourth step, training involves feeding the network a large number of labeled emails. So we feed the network with large amounts of data. No. Of labeled data. All that data is labeled. And when we have done so, we would consider the weights and biases of the labeling. Well, but really the weights between the neurons are adjusted through a process through backpropagation during the training process. Weights adjusted during training, specifically in the step of backpropagation. Biases, on the other hand, are also considered as well, hence our formula. Well, the biases, on the other hand, where the biases can refer to bias in many factors. And in biases, we consider the chances of error and can refer to data bias, selection bias, algorithm bias, accordingly. And now let me just move out so you all get an understanding. Feel free to take a screenshot of the steps. And let me just fix this part. And now let's go over the following steps for our specific program. So in this, what we will be doing is that one, after we have loaded the necessary libraries for what neural network we'll be calling upon, how we're going to train and test and split, we call upon NumPy, Keras, and scikit-learn accordingly to be able to call upon the necessary libraries that already have these robust neural networks and tools needed to be able to actually train and then test a following model. So what we do first is that we load one data set. We have features from our data set that we consider in our X and our Y will be considered our labels. And since we're doing binary classification, we do 1 for spam and 0 for not spam. When we load the email data accordingly with respect to the features as well as the classification we're looking for, and we're doing a binary classification. We split the data set into training and testing, and it looks like we're going to do an 80-20 split that we have with a random state of 42 to be able to have a fair assessment of when we were training the following model. So then we scale the features for better neural network performance using scalars, the standard scalar, and then we initialize the following model using a sequential model. And we have our layers that are over here, and looks like, oh, must be the fact that we are using one hidden layer. We have our input layer, and then we have our optimizer, and we got our output layer. There we go. And we are fitting the model by training the model on the scaled training data after we have already trained our given model within the given layers, even if we're using one or more hidden layers. In this case, we're using one. And we fit with the trained scale and the Y trained with 100 epochs and a batch size of 10, verbose of 1. And we evaluate the model on the testing data as well to consider that, hey, is this model actually creating the necessary predictions? And then we set our predictions for the model to predict based on the features that we have in our test portion of our data set. And so, yes, feel free to take a screenshot of this part over here. And then feel free to take a screenshot on our left side as well. Let me just clean this up for you folks. Let's get a better understanding. Feel free to take a screenshot of the coding assessment as well, and the whole practice problem. And now let's go over our second practice problem. And now let's consider our second practice problem. So in our second practice problem, we're considering developing a neural network for a bank to approve loans. As we know, with every single neural network, it's always going to be comprised of input, layers, and output. And for each neuron that we have, so neurons typically will have weights, biases, and activation functions. Which will all be woven together with an optimization algorithm. And neural networks, when it comes to the training of the layers, typically have an input layer, one or more hidden layers, and we have our output layer. So when we consider this, let's go over our following steps and dive straight in. So step one, we typically have to design the input layer configuration. So we need to figure input layer configuration. The second part that we have, first designing the hidden layers. The third part is going to be choosing activation functions. Or choosing the activation function. And finally, we train the network. So the first part for the features. So just like in our spam detector problem, we initialize the input layer and each applicant's data point becomes a neuron's input. So each applicant's data point becomes a neuron's input. We consider the features here. Then when we design the hidden layers, we structure the hidden layer to uncover financial patterns that might indicate a risk or default. So we uncover patterns to discover hidden patterns of a financial default. And the complexity here is tied with the range of financial behaviors and what we want to capture, so tied in with the features. Of what we want to capture. When we choose an activation function, that means is that in the context of the bank scenario, we might prefer the hyperbolic tangent activation function in our hidden layers for the centered range. So we would do the hyperbolic tan h activation function in our hidden layers for the center range. Because the hyperbolic tangent function differs between sigmoid because it also leaves room between the center point to make an accurate prediction, along with a positive and negative correlation as well. If need further context, by all means, feel free to go back to the activation function section for the course and garner further understanding. And overall, we can represent profiles efficiently, so we need to represent profiles efficiently. Then the fourth step is that we train the network. The bank's historical data trains the network, so we use historical data to train the network. Adjust weights and biases through iterations. And now, let me just zoom out and help minimize this to be able to help Gunnar. Let's clean out this so you get the full thing. Now, to go over our following program, all right, God, let me just fix that. Train the network, and now going over. Now going over our program. So first thing we usually do is that we import libraries, depending on what you want to do to be able to start. And we then assume we have a function to load our loan application data already. So typically we would just go in here to be able to start. It could be a CSV file of whatever format that we have. But the point is we have the data. We need to convert it to numeric standards. And depending on exactly between the features of what we want, so it could be credit score, it could be salary as well. The features would be set here, right in this area to be able to start prior to training, testing, and then doing the 80-20 split or 70-30 split as well. In this case, we're doing an 80-20 split. So features will be actually employed before we train or do the split. Give me a second, let me just clean this part up. So features would go here. We'll go here depending on what we want. So X would be the features, and Y can determine the output for classification. Yep. And after we did the split, we then normalized the feature data using we're doing a feature range using the tan activation function right here. So we are able to recognize this by using the min-max scaler to be able to scale the features that we have, and we use a feature range between -1 and 1. And the model that we're going to be using is a sequential model, and this is where our layers are going to be located over here. We notice we have the input layer, hence this name here, and we have one hidden layer. Then we have an output layer as well. Already set, so hidden and output. Then after we have already trained within the given layers, we then compile the model, and we are applying a loss function of binary cross entropy with, it looks like the optimizer is going to be used sigmoid in this case as the algorithm. So we do a feature extraction of using the hyperbolic tangent function to be able to actually have our features. And for the optimizer, we employ sigmoid, and we have metrics based on accuracy. We fit the model to our normalized training data with 150 epochs, a batch size of 20, and a verbose of 1. We evaluate the model's performance on normalized test data, since we did 80-20 split, to be able to test for the accuracy, and to have an option. We can predict the loan approval outcomes, and this will allow us to give us a probability of a loan being approved to be able to see exactly what would happen. So we would have a loan predictions, call upon that to be able to have a model predict on the normalized testing in particular. So we can just test to be able to see if a loan will be approved or not in that case, and determine the financial credentials, and have more flexibility since we employ the hyperbolic tangent function right around over here, hence the ranges between the features that we would extract compared to other activation functions as well. So that would just be in this context. So features are here, but they would typically be over here, and for further understanding as well. But we're employing the hyperbolic tangent function. And so, yes, let me just zoom out of here so you folks can be able to get a better understanding and see further. All right, and so yes, this was our video lecture for our topic of neural network structures. Thank you again for taking time to watch this. If you found this video very helpful, feel free and please do like and subscribe. And if you have any other questions as well, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye.